Hello, welcome to AT&T ThreatTraq for March 10th, 2015. This program provides network security highlights, discussion, and countermeasures for cyber threats. Today we're joined by John Hogoboom. As if I've never met you before. Today we're joined by John Hogoboom. Welcome, John.
Thank you.
And Matt Kaiser.
How's it
Matt,
going?
welcome. And we're kind of the regular local crew here today. And I guess Jim's perhaps out on a training exercise right now.
I think so, yeah.
So I'm Brian Rexroad, and let's jump right into it. And I guess we're always talking about manipulation of code and things like this. Who would have thought just flipping a bit could make the difference, right?
Well, this one is particularly fascinating to me. This it's an attack they're calling the Rowhammer bug.
All right.
Now this, the Google Project Zero team just released an advisory about this, and they're building off of work done by researchers at Carnegie Mellon and Intel Labs. The idea behind this is that there's physical effects within memory, in particular DDR3 DRAM chips, where when you read from memory, it can cause slight disturbances in adjoining memory because the scale at which you're operating is so small that you start having these weird electrical leaking effects around them. So the idea of rowhammering is basically reading from memory adjacent to memory you'd like to influence repeatedly to see if you can actually cause bits to flip. Now it seems that they found a way to fairly well repeatedly do this and chain it into an actual exploit against different platforms. They come up with two exploits. So the first one is against Google's native client, which is basically a way that Chrome can run native code, like x86, much faster. So it behaves almost like an x86 processor in a program. And it's got its own sandbox, so to prevent sort of the regular kinds of attacks you would expect, turns out they found a way to bypass that sandbox using some really clever modifications to jump calls in memory, relying on those bit flips to actually change a jump call from one location to another one outside of bounds of what the sandbox would normally expect, and there you go, now you're outside of the sandbox. The second one is against just a Linux kernel, and it seems that you can modify the page table entries, which is basically, I don't know how our viewers know, if they know about virtual memory, physical memory, but basically you're modifying where the computer expects to find different memory locations, so you can give the program control over its own page table, and then it gets to find where it gets to call, and then it's pretty much game over. So I mean, this is I find it most cool because this is physical, this is physics causing exploitation of software.
Yeah, there are a lot of things about this that I guess I can relate to a little bit. First of all, it's really kind of very similar to sort of a buffer overflow type of attack, where you're trying to inject code in a place where you didn't expect it to be, right? So sort of jump to a new place, you're basically flipping a bit so it changes where a jump goes to. It's very similar to what a buffer overflow is trying to do as well. Try to get something so it's jump into a place where it's executing code that it otherwise would not have executed, right? And one of the things I find very interesting about, you mentioned the electrical effects. That's really, as you said, the geometries of the memory elements are getting so much smaller, and really a DRAM's just a little capacitor. It's just a little place where you store charge. When you go to read that thing, you're just measuring just a few electrons. I'm not sure about the number at this point, but it's it's like handfuls of electrons they're basically stored in that capacitor, and to decide whether it's a 1 or 0. So if you can, based on the proximity of those, get some of those injected into a neighboring memory cell, there's a possibility of getting that type of an error to occur. And it's really a kind of a cool thing. We were talking about earlier how memory checking, the error correction codes, were actually reintroduced, I think on the order of maybe about 10 years ago. They had basically gotten rid of them, but years ago they used to have those, and it was partly because the memory elements were actually encased in, or the chips were encased in ceramic, and the ceramic had some radioactivity associated with it, and so a little, alpha particle or something could get in there and actually change what the memory was. And so in order to protect against that, they'd have a parity bit to see if there was an error or something. They didn't have the correction, but at least the parity associated with it. Very cool stuff. Yep. And so what do you think? Is this something we need to be really concerned about right now?
I think it just came out as of today's taping, and they've provided not exploit code but test code to show to determine whether or not the memory modules that are in your machine are susceptible to these bit flips. Now, they've tested about, I want to say, around 30 different combinations of vendor and memory, and it's not clear that this is a huge widespread problem. There may be certain platforms that have to be worried about. DDR4 is not susceptible to this. Memory with ECC is less susceptible. There's still a chance that if you manage to flip more than 1 bit, that the ECC is not going to be able to compensate for that, because I think it only really checks for
the probability.
parity, right?
Yeah, the probability of being able to detect it goes down as the number of bits goes up, but it's still. I'm not sure if they use 1 bit or multiple bits associated with that, but it's.
Did they say why DDR4 is not susceptible versus DDR3? What is it about DDR3? Is it something about the physical aspects of it? That
I'm not really clear on that myself. All I know is that somehow DDR4 is able to compensate against this.
Okay.
I'd be interested to find out the actual reason.
Yeah, I was
why
wondering if
myself.
somebody knew about it and maybe they engineered that in or something, but I don't know.
There's a possibility their correction coding is stronger. Again, as geometries continue to get smaller, they're putting more protections in place for this kind of thing, this eventuality. Actually in disk drives, they've done something very similar, added error correction coding that didn't exist previously because the geometries are getting so much smaller, and you'd expect that there's going to be some probability of some sort of an error. And it kind of brings to mind our own minds. They're one of the, I guess, the most complex computing platform that exists, but it has errors all the time. There are just so many things going on that they get jumbled up, and I think this is just that that next step in the evolution of things, where things you have to build in tolerance for errors as a part of the platform, and this is a case where they've demonstrated how it could potentially be used for malicious purposes, mind manipulation.
Well, being a software developer, you should always code in for the possibility of errors into your code to check for unexpected
That's true too.
things to occur.
The question would be, do we have to start coding to protect against errors in our own hardware at this point? Do you have to double validate everything you've saved to memory when you pull it back out is really what you'd save to memory in the
Well,
first
I guess
place?
within reason, right? You don't want to sacrifice performance too much, to have a perfect situation with your error correction, but to some degree, I would say
you
yes.
should be able to rely on the hardware. I mean, it's in fact, ultimately, you want to be able to trust what's coming out of it. Otherwise, what can you trust? That's really.
Well, I mean,
kind of
I
the
would
core.
put that at the hardware level. That kind of like the firmware or something would be checking for whether there's an error. Not in my software would I be not trusting the memory that's in my machine. I wouldn't, if I'm writing something in Java or whatever. But in general, I'm just saying code in general should always have error checking for whatever it's doing with its own stuff.
Yeah.
There's one more parallel that I thought was kind of interesting. Single bit flips. There was research done a couple years back on single bit flips in DNS. I don't know if you remember that one, but it turns out that if you take a popular domain and occasionally somewhere along the transmission line a bit will be flipped when a DNS request and it becomes like Foogle.com instead of Google. If you go ahead and you register Foogle.com, you will get a significant amount of traffic that's destined for that other domain. And there's really not much to be done for that. I mean, you can set up your own little traffic collector, and simply because of a single bit, you're going to start getting significant.
Yeah, it's actually an interesting one, because the likelihood of getting a bit error in transmission where it's gone through a lot of systems along the way is greater. In fact, the whole IP network, internet, is based on sort of a best effort delivery activity, with the expectation that some of those packets aren't really going to get there without some kind of a munging. But DNS uses UDP. It doesn't have it has some header error checks, but it doesn't necessarily validate that the packet itself that's left to the end system, and I don't think DNS did a whole lot to make sure that it got delivered without some.
And again, that's a performance reason probably. That's why they use
it's
UDP.
performance, yeah, absolutely.
Completely for performance aspects.
Yeah. So that's why we overlay it with SSL certificates to make sure that we're talking to who we think we're talking to, and that the domains match up, and then ultimately put encryption on top of that, which it helps to maintain the integrity. You pay for it in performance. That's right. It's there's no free lunch. No. And speaking of no free lunch.
Oh yeah, good segue. The story I was covering today is a little bit more pedestrian than Matt's story. It's not as brainy.
Clever. I have to say clever.
Well, clever. probably not unexpected. If you're a bad guy, this is a great idea. So a lot of people have probably observed certain websites that they go to and they try to view the source, that it's obfuscated. A lot of people, when they develop their own code for their website, they want to protect it from people just viewing the source, taking it, using it for their own purposes, especially JavaScript and whatnot. So there's a lot of code obfuscation services out there, programs that'll obfuscate your JavaScript or even your page in JavaScript so that it renders. If you go look at it, it's just a jumble of JavaScript. You can't really understand it. It's a lot of obfuscated code paths, very hard to follow, but JavaScript knows what to do. When it reads it, executes, it can unpack it and render it properly in your browser. Similar probably in a way to, Java uses a, it's not an obfuscator, but it packs it so that it's not easily readable. It's not like a text kind of thing. In any event, somebody out there figured out a way, or thought about it and said, well, why don't we offer some free code obfuscators, and people can obfuscate their code, but when they do that, we're going to bundle in a little extra something in there. So the problem is when you do that and you take all of your code that's easily readable, you obfuscate it through this tool, now you get back this jumbled mess that you have no idea what it's really doing.
It's not exactly open source anymore, is it?
No.
It's not even open to you. Your own code.
Yeah, your own code is not even readable anymore.
Right.
But you could take that, put it on your website. If a browser hits it, it gets all deobfuscated, rendered in the browser. But even if you do a view source, you're just going to see the jumbled mess.
Yeah.
So what they were able to determine is some bad actors out there have been, when they go to obfuscate your code, they slip a little bit of their own stuff in there that's going to inject ads or spam or other pop-ups along the way. So now when your visitors visit your website, they're getting your website, but also another little nugget down there that's getting, pushing spam and whatnot to your
now,
to
as a
your
website
browser.
developer, I guess there's the opportunity to find this out while you're doing testing, but otherwise you're dependent on somebody actually complaining about it or something along those lines, right?
The other interesting aspect is they did some examination of, well, how much of this bad obfuscated code is out there that's injecting this bad stuff into the pages. And they noticed that there's at least a few people who write like plugins for WordPress, which is a common thing. So I've got a WordPress plugin that I wrote. I want to protect it. I want to be able to sell it. Maybe I charge people $5 or something for it to deploy it onto their WordPress website. So I don't want them to just be able to read it and just dump it themselves or make modifications to it. So there are a few of those out there where these plugins are being distributed with this obfuscated, they've been obfuscated, but the developer who developed it doesn't know that there's this bad injection that's been stuck in there. So something to be aware of, not only in your own code when you try to use these obfuscations, but if you use some of these content management systems like WordPress and you're pulling in plugins from other places, you might want to make sure that this plugin is trustable. Because even though the person who wrote it might be trustable, he might have tried to obfuscate his code so that you can't see it to protect himself, but he didn't know that he was getting had by some of these guys that are, doing this bad activity with their obfuscations.
So it sounds like a point where apparently they didn't even have a desire to be transparent about what they were trying to do. It is, ultimately, it comes right down to that discussion about there is no free lunch here. These folks, they're trying to provide a service, they're trying to earn some money as a part of their service. The question is, are they letting you know that they're earning money as a part of their service, through whatever means and how they and how they're conveying that to you? But,
Right.
It's I guess ultimately it's if you get something for free, you should be paying some attention to what the motivation is behind these folks. There really is no free lunch. They've spent time and effort putting together these things or providing a service. They have to pay for it somehow. They have to feed their families perhaps, but again, it becomes a matter of transparency. Did it say in the fine print perhaps that they were going to be sticking those ads in there?
Right, and who reads the fine print? When they give you like 80 pages.
There's an awful lot of fine print going on these days,
Right.
So, speaking of fine print.
So this is a bit of a two-parter. There's just two articles that I found particularly interesting.
Yeah.
The first is an article by Didier Stevens. I hope I'm pronouncing his name right. He's been looking into Microsoft Office vulnerabilities and exploits for a long time. He recently found a campaign where instead of using the regular Office extension, a .xls or XLSX now, that's right, the new ones. That's part of the point. Certain XML files, if you open it up in a Windows machine with Office installed, it'll just treat it like an Office document and try and do its best to open it as a Word file or a spreadsheet or something like that. And it turns out that when it does that, it'll try and unpack certain portions of it, and then there'll be Visual Basic code in there that'll reach out, grab a payload, and execute it. So this is an XML file, and it's as far as most people would be concerned, XML is nothing but structured text. You build the right structured text, you feed it to the right program, you've got yourself an exploit.
Right. It's a matter of how the programs interpret whatever they're consuming. Every time we have a discussion on these kinds of things, I can't help but think back to the good old days with the von Neumann architecture, where there was a very clear distinction between code and data.
Yep.
And as soon as we went down this path of kind of blurring the two, that basically a file name tells a program how to execute on something. It made data something other than just data. And so we have this whole entanglement and opportunities for taking advantage of it.
Well, actually, we at AT&T have an even earlier prior art for that, when we had signaling and voice calls in the same, on the same phone lines.
Yeah.
But that's when
We went through a lot of trouble, in fact,
Yep.
to create the SS7 network, to be able to do all the control stuff out of band.
Out of band.
Exactly.
And to be able to get away from it. It was the tones. I mean, still the end user dialing was still in band effectively, the DTMFs and the click dials or whatever. But ultimately, in the network itself, the signaling was done out of band. And the internet doesn't really have an out of band network. It basically tries to create channels within the network itself. So it's possible to control these things. It's just a matter of you need some sort of a structure to work within. And I guess my feeling is that some of that structure is really it's almost become too flexible. You almost really kind of have to go back to some basic rules about how to create systems and architect them in a way that they can be more secure. So in the meantime, we're going to stumble through.
So that was the first article.
Yeah.
The second one is very similar. Bitdefender found a Cryptowall campaign that was distributing an attachment that was a CHM, which is a compiled HTML file, which Windows uses as help files. And they're basically HTML pages that you can open up in a very specific browser, but it can still run JavaScript. And from there, that's where you have problems where JavaScript runs, it goes out and grabs another file and executes it. So it was two stories in a pretty small range of time that both had to do with sort of trustworthy
similar
file
kinds
types.
of things. Yeah, and I remember back, some of the early pieces of malware were conveyed as screensavers, right?
Oh yeah, and they still are. We still occasionally see .scr files.
Yeah, absolutely.
And we've seen even in like the doc and XLS space, the whole notion of VB script coming more into play. Like they used to do that a long time ago, and they went away. And now, within the past year or so, we're seeing more evidence of that. And they just, even though your Word, Microsoft Word protects you and says, hey, there's a script in here. Are you sure you want to click it? The guys, the bad actors have figured out, hey, put in a big arrow here that says, in order to see this text, click on the Enable Scripts button right here above the screen here. So a lot of people click it. So you got to be, any program, like you said, any program that's reading a file in, no matter what that file is, it could be Notepad. People think a text file could be benign, and for the most part it is. Notepad's somewhat bulletproof, but it's a program that's interpreting data, and if you could give it just the right amount of stuff that program doesn't know how to ingest whatever it's reading, you could hit a buffer overflow like we talked about and get some arbitrary code execution to occur.
Yeah.
So even though it's not intended to be a scripted language, you could put that in if you can trick the program that's reading it, because pretty much everything is read by program.
Yep.
That reminds me, there's a really good book on the subject of exploit writing called The Bug Hunter's Diary. And there's a whole bunch of really mind-blowing examples. Like, I think one of the bugs in there that he exploits is he feeds a specially crafted video file to VLC player to cause it to crash and then build an exploit around that. So it's basically any program that takes any input, whether or not it's text files or video or who knows what. There's a possibility that you're going to be able to craft something that'll change the way that it behaves.
Yeah, absolutely true. And it's always looking for those boundaries that weren't considered.
Right.
Like a frame size of 0.
Yep.
Right.
That just sends the thing into some berserk mode, and if you can control the berserkness, it becomes an exploit. So we'll shift from exploits into something, I guess, really a little more innocuous. We'll take a look at the internet weather for the last week or so here. And we hadn't reported on this sort of activity recently, but there is sort of an increase in it. This actually shows up as scan sources on port 17788 UDP. This is associated with PP Stream, which is basically like a point-to-point streaming protocol or application, I guess it is, popular for Chinese programming apparently. So we see an increase in the number of sources, the number of participants that are taking place in that. I suspect that what this is, either is something of significant interest that's popped up and you've got more viewers that are partaking of it, or perhaps there was a sort of a shift in the server infrastructure that's associated with this particular service. But in any case, there seems to be an increase in that activity. It appears to be innocuous. If you see that on your network and you're concerned about it, you have to make some decisions about whether that's acceptable on your enterprise network, for example. And there are some pointers on the internet about how you can control this type of activity on your network. Port 17788 is one of those ports that it depends on. Next item here is bytes on source port 161 UDP. That's Simple Network Management Protocol. The theme here is this appears to be, from my memory and experience, one of the largest reflective denial of service attacks that I have seen using SNMP. This particular one happens to have been going on for a few days, so it's large in that sense, but it's also large in terms of the number of the amount of bytes that it's generating, on the order of gigabits per second. I think most of the cases we've looked at in the past have been way down in the maybe 100 megabits per second or something like that. And you see some of these examples in the past. I guess there's one that went up to about 4 gigabits per second. But
well, you're looking at bits per hour here, though.
Oh, yeah, actually, maybe we should correct that. It's a good point. So it is relatively smaller than that. So good point, John. But in any case, it is one of the larger attacks that we've seen on this in this activity. Happens to be targeting a site in China, and so it's not an immediate threat to within the United States, but certainly one to be considering the vectors of denial of service attacks.
It's pretty well sustained too.
It's well sustained.
It's a long duration, longer than we usually see attacks go on for.
Much larger than usual. So this probably is in the hundreds of megabits per second once we account for the fact that it's really showing per hour. The top 10 most probed ports here, we see there's been a shift here. That is, we're seeing port 22 on the top. We had been seeing port 23 on the top, so port 22 followed by port 23, then 443, which has moved up significantly, relatively speaking, and then 1900 UDP. We're going to take a little closer look at port 443, by the way. 1900 UDP, that's associated with reflective denial of service attack activity. 445 TCP, the configure stuff. 53 UDP, again, probing for DNS or associated with reflective DDoS attack activity. Port 135 TCP, we're still seeing activity on that port, which still baffles me that we see that, but it apparently continues. And then 1433 TCP, that's probing for Microsoft SQL database. 3389, that's remote desktop protocol, and then 8080 TCP, likely looking for proxies. So taking a little closer look at port 443 TCP, this is a little different than I typically show because this is where the anomaly really shows up. That's in scanned packets on port 443 TCP. And it's very unusual to see this type of behavior, but in this particular case, it's really a SYN reflection attack. It appears that the source address is spoofed in this case. They're spraying out SYN packets to a lot of different target addresses, and then waiting for the SYN ACK reflections to come back and then actually go to the original target associated with this. There are multiple sources, and this is one of the first cases I've seen in a long time. And the indicator of this is, again, simply, in fact, in a lot of cases what they do is they get SYN resets back. It doesn't even matter if they get a SYN ACK. They can get SYN resets back. And as a consequence, this target would be flooded with relatively small packets, but a lot of them because they're repeating this over and over and over again. Looking at the top 10 most sources doing probing, at the top of the list, port 23 TCP, followed by 445 TCP. I tend to skip over the ICMP protocol, by the way, partly because there are a number of contributors to it, and it's not necessarily a good, strong indicator unless you actually dig into where that activity is coming from and more specific characteristics of it. But again, 27015 UDP, and then followed by 6881. That's associated with BitTorrent, if I remember correctly. 1900 UDP, which is that reflective denial service attack activity. And then find the 3159 UDP, which I believe was a proxy protocol. Is that right?
I don't remember.
Yeah,
we looked it up last time too, and we couldn't remember last
Tell me
week.
that's
I'm getting mixed up these days.
Yeah, I think it's the
Naviga
Naviga web.
Yeah.
Yeah.
All right, so I thought it'd be worth taking a look at, again, a little bit of the history associated with port 23 TCP, because it is at the top of the list here. We're looking at 90 days of activity. And again, we're looking at the number of sources. And as you recall, we were, seeing some botnet activity predominantly associated with Internet of insecure things, those unmanaged devices that don't have good patching practices and often have default passwords and unfortunately allow these malicious actors to kind of walk into them and use them for bots. The number of sources that are doing the probing is actually down. In fact, the number of probes is down somewhat as well. It's certainly not gone. There's a significant amount of activity taking place there. We're measuring thousands of sources here, and so we've kind of leveled off at around 40,000 sources at any given time in the day. But it is down relative to what we had seen over the last 90 days, which is, I think, an encouraging sign. I don't know if there have been some actions to basically deter some of this activity, or if it's just simply that they're laying idle for a while, but nevertheless less activity than we had seen previously. And that's our show for today. I'd like to thank you for joining us, and if you'd like to get in touch with us, you can email us at threattrack@list.att.com, and you can find ThreatTraq on the AT&T Tech channel. It's att.com/ThreatTraq. It's also available on YouTube and on iTunes. You can follow us on Twitter. Our handle is ATT Security. And I'd like to thank you, Matt. Thanks, John. I enjoyed the conversation today. And I'm Brian Rexroad. We'll be back next week with a new episode. And until then, keep your network safe.